Please tell us about your research in super simple words, please.
Yeah. So the motivation of my research, number one, is green chemistry. So what we want to do is we want to make chemistry more sustainable and also safer. And we want to produce less toxicity. So those are basically the basic ideas of green chem. And then we can approach green chem throughout different, we can use different tools to achieve green chem. And what I do specifically is catalysis. So I design nanoparticles that can be used to make chemical processes, more sustainable and greener, because catalysis is in almost everything that we do. Almost chemical product is made through a catalytic process. So if we change a little bit catalyst, we can change a lot the process. We can, use less energy to make the products. We can, have higher selectivities, produce less waste. We can change completely the products that we have. So, small tweaks in catalytic systems, they can make big differences. So this is what we try to do. We try to, find where we can change the catalytic systems so that we change the reaction as a whole and we make them greener in some way. Yeah.
Mm-hmm. Mm-hmm. Okay, that's interesting. So when you say greener reactions, are we talking about making the renewable energy reactions more efficient, or are we talking about some other field, so not batteries or not renewable energies, and making the reaction, like the chemical process, more green? Like what do you mean when you say green chemistry?
Yeah, so it's a very broad theme. So it depends on what exactly you do. Like in my PhD, I worked mostly on reactions that are important for the pharmaceutical industry. It's an industry that is highly wasteful. If you think about, if you look at the E factors, which is basically how much waste is formed per product. In the pharmaceutical industry, you have like 90% of waste and 10% of product usually. So it's nonsense. It's because usually the molecules, they're very specific because they need to play very specific roles. Mm-hmm. So putting them together is not that easy. So usually you need many steps, and each step has a small yield. So you go decreasing the yield. So you produce a high amount of waste. You have to purify the products all the time. So it's highly wasteful. So this is why in my PhD we approached pharmaceutical industry. Uh-huh. So I looked at two processes specifically. So one of them, we were making rose oxide, which is a fragrance that gives the smell of roses. It was really nice because the lab was smelling good for once. So I liked working with this reaction. But this is a multi-ton scale process. So it's done, it's the fragrance that is used the most in the cosmetic industry. And we can make it using a photochemical step. So we can make one, a key transformation using the energy of light. So this is in the scope of green chem because, we're using light, which is abundant. And doesn't and inherently like safer than, let's say, heating reactor or things mm-hmm. like this. Mm-hmm. In another project I used I was producing like amines, which are molecules that have lots of applicability to make medicines. For instance, they have a lot of activity in the nervous system. If you think of like methamphetamine, anything that we think about amine, they really have high activities in our bodies, and we could make them, but then it's a multi-step process as well. But what we managed to make it in a one step, and to really like use the bits of molecules that we leave that would be waste. We can incorporate them again. And, like make the process more, more one pot, like more efficient, let's say. Mm-hmm, more mm-hmm. What we say in green chemistry, we talk about atom economy. So, out of all of the atoms that you put in there, we try to incorporate as much as we can in the end so that we don't have too much waste, you see.
Oh, wow. So basically green chemistry can be used in any industry where there's a lot of waste.
Anything.
Oh wow!
Yeah.
Where we can use. Sorry, go ahead.
Yeah. In my postdoc now, the group that I'm working on. So I just started, so I haven't really, worked a lot in their themes yet. But they are known for doing biomass transformation reactions. So they work with lignin, which is the part of food that is usually hard to work with, and they have methods to stabilize it, and then they can, extract very high value chemicals from this biomass that is usually waste. So there's many ways that you can approach green chemistry differently.
Okay, interesting. You know where we can definitely use green chemistry? I recently recorded, the movie Glass Onion, and
I probably know the movie in Portuguese.
Okay, probably.
But I know what you're talking about.
Yeah, but the content would be the same. So in that, they claim there is this clear crystal, which is like zero carbon emission, and it's like super cool and hydrogen fuel and da 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 da. And we recorded a podcast we recorded a video rather with like the science behind Knives Out, and in that one of the points was, it's ridiculous at this point, like as of today, making the hydrogen fuels or making the hydrogen fuel cells or this clear crystal. It's not environmentally friendly. Not environment. I should not say that. It's not green. It's not like creating this crystal or synthesizing this hydrogen fuel is emitting a lot of carbon dioxide because we don't have any process. So I think that's where we will definitely need you and your group to step in.
Exactly, and this is really like something that we talk about in Green Chem as well. We talk about cradle to gate, that we try to think about our processes. So from the beginning, or when everything, the raw materials are sourced from nature, until when they are disposed. So this is like, ideally we should think about green chemistry looking at this whole process, but it's difficult for us to do the whole thing. So we try to break it up, so we look into specific steps, but ideally Green Chem talks about this whole process, like looking at where we source the materials and how they are disposed in the end, and we try to really do like smart chemistry. We have the resources, we have the tools, we have to put them together, in a smart way to make things work out. Yeah,
I mean it's really interesting for sure. So which are the industries, I mean, now that we have the expert on the podcast under the microscope, which are the industries which could use green chemistry sooner rather than later? You already mentioned the pharmaceutical industry, where 90% of the chemicals are disposed of and only 10% are useful or valuable. So which other industries are the ones which definitely could use some help of green chemistry or making their chemical processes more greener? Which other industries are there?
Yeah, so it's very broad to say to making them greener. So like every industry we can make the processes greener.
I know.
In different ways. I think like the pharmaceutical industry is the one that I focused a lot on my PhD, really because it's screaming the amount of waste that they produce. And there's also like use of solvents. For instance, most of the waste that we form in chemical reactions are from solvent use, which is insane because the solvent is not, we usually don't think about the solvent when we're thinking about a reaction, because the solvent is just there, theoretically assisting, but it's usually most of the waste that we produce. So those are things that we look into a lot. There's, of course, the petrochemical industry, which is, incredibly efficient on the way they do everything. So those are reactions, that work very well. We have a lot of infrastructure for it. Theoretically, it's a very efficient process. There's not much waste or anything. The problem is like the raw material that we use, right? So every industry, we have to look into different aspects of it. Yeah.
Yeah, that makes sense. And now that you say it, when you said solvents, I was reminded of how much solvent we used when I was doing my master thesis, for example, or even PhD, but mainly master thesis, while cleaning the substrate. So we used like 250 ml of acetone 3 times, plus 250 ml of isopropanol one time. So it's just a lot, and we had like crates and crates or buckets and buckets of acetone, and we had buckets. And I know that acetone is probably not the solvent. That's not what you meant, but I'm just thinking from the chemicals perspective.
No, but that goes into it as well. I mean, purification columns is just so this is why what I do, like in my projects, we usually do catalysis in a heterogeneous way, which means the catalysts are usually like solid, and heterogeneous just means that the catalyst is not in the same phase as the reaction media. In my case, I usually use solid catalysts. And I do the reactions in the liquid phase so that I can separate the catalyst by filtration, or in some way. For example, I worked with magnetic materials, so I could separate them magnetically. So you don't have to run, those columns to purify from, from the catalyst, because the catalyst is usually like, most times you use metals and, like scarce metals, toxic metals, that they do a great job in catalyzing the system, but of course you don't want to keep them in there, otherwise they're going to be they're going to add toxicity to your system. So we need to find ways to separate. Heterogeneous catalysis is a good way to do this, because the catalyst is solid. You can let it settle. You can track it like magnetically. You can filter. You can centrifuge it. There's many different ways to look into it. Yeah.
That's a very good point. And for everyone who does not or who hasn't understood what heterogeneous catalysis means, just to give like a very simple and non-relatable or relatable example, so to say, is that if you have water, and if salt is your catalyst, water is your solvent, it's in liquid state, and salt is your catalyst, let's assume that. And so what you do, or what you could do as a heterogeneous catalysis approach, is like you dunk a giant crystal of salt in the water, so let a part of the salt be dissolved in the water to whatever extent, 5 minutes, 10 minutes, and then take the solid crystal of salt out. So that means it's easier to remove it, instead of putting like ground salt, like the normal salt, in the water and letting it all dissolve. Does that make sense? Did I give a good example?
It does make sense, but I think a better example would be, let's say if you get like a fine salt and you put in water, it would dissolve. So this would be, like homogeneous catalysis. But let's say you use sand instead of salt. This would be heterogeneous. So if you use sand instead of salt, after you can separate the sand from the water.
That is. Yeah, that's a good
because
point. Yeah.
in the example you gave, when the part of the salt is like being dissolved, actually like it would be homogeneous catalysis, because the salt that is actually doing the catalysis is the reaction is the one that is in the system. But those are boundaries of there's a lot of discussion on what is homogeneous or heterogeneous, but I think the sand example is good, because after you can separate it, there's no sand left in the system. You can filter it and let it settle.
Yes, thank you for explaining that. That's a very good point, because in my head, heterogeneous catalysis only meant that instead of using a liquid catalyst, you use like a solid catalyst in this particular example. But you're absolutely right. It's not just about that. The homogeneity goes beyond just the phase, or liquid or solid, or whatever.
Exactly. Yeah.